Ever since we first looked up at the night sky, we've had this one huge question, right? Is anybody out there looking back at us? It's probably one of the biggest mysteries there is. And today, we're going to tackle it by looking at a really cool scientific tool that was designed to do just that. So let's dive in.
I mean, this is the ultimate question, isn't it? It's the stuff of science fiction, it gets philosophers talking, and it sparks that deep down curiosity we all have about our place in the cosmos. For like ever, it was all just guesswork, pure speculation. But you know what? That's actually starting to change. For decades now, we've been building these absolutely incredible things. Think of them as giant electronic ears, and we've been pointing them straight up at the sky. We are actively listening, just hoping to catch any kind of signal, any sign at all that we're not just talking to ourselves out here. But let's be real, this feels like a ridiculously huge question, doesn't it? The galaxy is just so vast and time is so deep. How on earth could you even begin to put a number on the chances of another civilization being out there? Well, what if I told you there's a way to break that enormous question down? That's exactly what one brilliant astronomer figured out. He gave us a tool to do it. So the secret here, when you're facing a problem that feels impossibly big, is to chop it up. You break it down into a bunch of smaller, much more manageable questions. Instead of taking one giant, wild guess, you just take a series of logical steps, one after the other. Okay, so before we go and tackle the entire Milky Way galaxy, let's bring this right back down to Earth with a simple analogy. Imagine we're trying to find one very specific type of student at a huge university. And here's the catch. We can't just look at the student records. So we're not just going to pull a number out of thin air. No way. Instead, what we're going to do is create a series of filters. We'll start with the total number of first-year students, and then we'll just apply one filter, then another and another, using probabilities to narrow down the crowd. Let's see how this actually plays out. All right, so first things first, we need our big starting number. Let's say this university has 12,000 brand new first-year students. That's our pool. That's our starting population. Okay, time for our first filter. What percentage of these students you think are studying fine arts? Let's go with a reasonable guess, say 10%. And boom, just like that, our massive pool of 12,000 candidates drops all the way down to just 1,200. All right, next filter. Let's narrow it down by gender. Of those 1,200 fine arts students, what fraction are female? Let's estimate maybe 60%. And again, just like that, we're down to 720. Okay, now for another trait. What's the probability that one of these students has red hair? Well, that's pretty rare, right? Maybe about 2%. And whoa, look at that number now. We've gone from our starting 12,000 all the way down to just 14 possible students. And now for the final filter. How many of them are left-handed? Well, that's about 10% of the population. And suddenly, there it is. Our massive, complex problem has an answer. Out of 12,000 students, we can reasonably expect to find just one person who meets all those criteria. See how that works? By chaining these probabilities together, you can take what feels like an impossible guess and turn it into a pretty solid estimate. And this right here is the brilliant part. Back in 1961, an astronomer named Frank Drake had this amazing realization. He figured you could use this exact same step-by-step filtering method, but instead of looking for students in a university, you could use it to search the stars in our galaxy for something far more elusive. So what he did was create a framework, kind of like a roadmap for our cosmic detective story. And the key thing to remember is that it's not really designed to give us a single final answer. Its real purpose is to organize our ignorance, to show us what we don't know and which clues we need to go out and find. And it's called the Drake equation. So this is a simplified version of it. See that N at the beginning? That's what we're solving for, the number of civilizations we can talk to. And it's the result of multiplying these four key factors together. It's just like what we did with the students. Each piece of the equation is another filter that narrows down the possibilities. So really, the whole thing boils down to understanding these four clues. First, we start with the number of potential crime scenes, if you will, all the habitable planets out there. Then we have to ask, okay, but on what fraction of those does life actually get started? And then, of those, how many go on to develop a full-blown civilization? And finally, and this is the really tricky one, how many of them are around right now at the same time as us?
Okay, let's take a look at that first part, NHP. This is probably the number we feel the best about. I mean, our galaxy has over 100 billion stars, and what we're discovering now is that planets are like everywhere. They're incredibly common. So it's very, very possible that there are tens of billions of potentially habitable worlds right here in the Milky Way.
So we've got all these perfect stages set for life to begin. But what's the chance the show actually starts? That brings us to our next variable, life. The interesting thing is, here on Earth, life popped up surprisingly fast once the conditions were good enough. That might hint that it's a pretty common thing. But, and this is a huge but, Earth is still the only example we've got. It's a data set of one.
All right, the next clue we have to investigate is F-Civ. That's the fraction of planets with life that go on to produce a technological civilization. And this is where scientists really disagree. The conservative view? It's that we are just an incredible fluke, a 1 in a trillion shot, the result of a super long chain of cosmic coincidences. But the more optimistic view says, hang on a second, evolution tends to find similar solutions to similar problems over and over again.
And this leads to a really cool idea called convergent evolution. This is kind of the optimist's best piece of evidence. Think about it. A shark is a fish, and a dolphin is a mammal. Totally different branches of the tree of life. Yet they both ended up with that same sleek, streamlined body shape. Why? Because it's just the best solution for moving fast in the water. So the optimists argue, hey, maybe advanced intelligence is just another one of those winning solutions that evolution is bound to stumble upon, again and again, all over the universe.
So, okay, let's say these civilizations are out there. How are we actually looking for them? How do we tune in to the galactic conversation?
Well, back in 1959, a couple of physicists had this big realization: radio waves. They are the perfect cosmic messenger. They can travel for light years and light years across the galaxy, and they pass right through all the interstellar gas and dust that would totally block regular light.
But which channel do you listen to? The radio dial of the universe is enormous. Well, this is where the genius idea comes in. Scientists decided to listen at a very specific frequency, 1420 megahertz. Why there? Because that's the natural frequency where cold hydrogen gas, which is the most common stuff in the entire universe, emits a little bit of static. Any advanced civilization out there would know about this frequency. It's like a universal meeting spot, a cosmic water cooler where everyone knows to gather. And that brings us to the last variable in the Drake equation. And honestly, it might be the most profound one of all. It's the one that transforms this whole thing from a question about astronomy into a question that's deeply, deeply human. That final term is F now. And this fraction depends entirely on one thing: the average lifespan of a technological civilization. Do they figure things out and last for millions of years, spreading across the stars? Or do they discover powerful technologies like radio and nuclear power and then pretty quickly destroy themselves? You could see how that number could end up being very, very small. And that right there is the ultimate takeaway. The Drake equation, it's like a mirror. It shows us that in our search for intelligence out there in the cosmos, we're forced to look right back at ourselves and confront our own future. The biggest unknown in this whole cosmic puzzle isn't about biology or astronomy. It's about us. The final question the equation really asks is, how long will our signal last?